So we begin by continuing with our study of maps and specifically one dimensional maps. So recall that the kind of discrete time dynamics we were looking at was a map function of the form xn plus 1, a sum function of xn, and x naught is defined to be in some interval, but we started off by defining it to be on the reals, and then the question was to study the dynamics, if you like, implied by this discrete time evolution equation. Before I do that, let me settle a couple of questions which were asked last time, the first of which had to do with what happens if this map function itself changes with time. In other words, if at the end stage you have a different map function each time you iterate, this of course would be the discrete time analog of a non-autonomous system, where the evolution equation would explicitly involve time on the right hand side, and we are not looking at such maps to start with, although one can in principle do so. We are not going to do that at the moment. So we are again looking at autonomous systems which do not have this possibility here. The second question that was asked was much deeper and had to do with whether in the presence of chaos, which we have not defined as yet very clearly, you could have order as well from chaos. And there the comment that I would like to make is that the lesson taught to us by chaotic dynamics is that simple evolution equations, simple dynamics could have very complex solutions. So very simple looking equations could lead to very complex evolution, very complicated evolution in time. The solutions could be extremely complicated. The other thing is also true, namely you could have a very complex system and on the average it could behave in an extremely simple fashion. For instance, if you took the gas particles in this room, the motion is certainly chaotic at the classical level, highly chaotic as we will see, and yet there are very simple average laws such as the ideal gas equation of state PV equal to RT and similar laws which represent the behavior of macroscopic average quantities. Those could under suitable circumstances, under special circumstances, be actually extremely simple. Another example is you take a piece of metal and you apply a voltage to it and you have a current in it in a conductor, and the current is proportional to the applied voltage, very simple Ohm's law. This again is in spite of the fact that the individual charges inside the electrons could be doing very complicated things, and yet you have a macroscopic law which is very, very simple, or Hooke's law in elasticity, or Fick's laws of diffusion and so on. All these macroscopic laws are quite simple to write down, but they refer to average or macroscopic quantities, and they come out by averaging over a large, very large number of individual microscopic motions which could themselves be very complicated. There are reasons for that as well, and a little later when we talk about invariant densities I will come back to this and talk about thermodynamic systems and what is so special about them. The third question that was asked, again jumping ahead a little bit, was whether you could have simultaneously coexisting in a system both regular motion as well as chaotic motion, and the answer is yes. In general this is possible. There could be regions of phase space in a dynamical system where if you start with an initial condition in one of these regions the motion remains regular, non-chaotic. On the other hand, there could be other regions where the system behaves chaotically. This is entirely possible. We even talked about this in the context of Hamiltonian systems where something very special happens when you have chaotic motion, and I will return to this a little later when we talk about chaos in greater detail. And if you recall, in Hamiltonian systems which are integrable, the motion is on n dimensional tori in general for an n freedom system, and if you took the example for instance of n equal to 2, then the motion in a 4-dimensional phase space is restricted to 2-dimensional tori, and they could pictorially, I could draw them as in this fashion. Perhaps you have one torus like this and there is another initial condition for which you have a larger torus of this kind, and these tori are nested within each other. It is entirely possible that in the region in between two tori you have chaotic motion, irregular motion, but since these tori split the whole of the space into an inside and an outside, remember the energy surface in this case is 3-dimensional in a 4-dimensional phase space, and a 3-dimensional space is split into an inside and an outside by an object like this torus, anything that is inside can never escape outside, and so the chaos is actually contained in the region between successive tori if it happens. As soon as n becomes greater than 3, greater than or equal to 3, then the phase space for 3 n equal to 3 for instance, the phase space is 6-dimensional, the energy hypersurface is 5-dimensional, and the tori are 3-dimensional tori, and these tori cannot split up this 5-dimensional space into an inside and an outside. So all the chaotic regions can actually be connected to each other, and you have what is called a stochastic web or Arnold diffusion, which takes you from one point of this stochastic region to another, and that goes through all of the phase space, which is not striated, which is not contained, which is not occupied by the tori themselves. So this kind of behavior can happen, could be very, very complex, and certainly coexistence of chaos and regular motion is possible in many systems. Okay, now let us go back and look at some of these maps in a little greater detail. We talked about the fixed point of such a map. So a fixed point at x star implies is a root of x star equal to f of x star, and it was stable if mod f prime of x star was less than unity, unstable if it is greater than 1, and marginally stable or indifferent if it is exactly equal to 1. Okay. So these fixed points are the analogues of critical points for continuous time flows. What happens if you have a fixed point of the following kind? What happens in a map if the point, let us call this point A, if you have A equal to f of b and b equal to f of a? What happens if you have a pair of points A and B such that A is f of b and b is f of a? So it is quite clear immediately from this, this implies that A and B are fixed points of the iterated map. F of x, which I will denote by f2 of x. They need not be fixed points of the map itself, but they could be fixed points of the first iterated map. So you take this initial point, you take the value a, then you calculate what f of a is, and turns out to be some number b, but you calculate f of b and you are back to a. So this is entirely possible. What would you then call the pair A and B? It is clear that under iteration A goes to B and B goes to A, it keeps coming back. What would you call such an orbit? It is the analog of a closed orbit in continuous space. It is a periodic cycle, and such a thing is called a period 2 cycle, AB. We are going to look at examples of this very shortly. So in this staircase construction that we had, or even this cobweb construction we had by the method of successive approximations, it would turn out that the point, the function corresponding to the initial value A is something, some B, and then to the value B is back to A, and they form a period 2 cycle. When would such a cycle be stable? Well, it is clear that it would be stable if the slope of this function, this is a new function now, it is the function of x, it is a new function, if the slope at the fixed point of f2 of x is less than 1 in modulus, in magnitude. This is exactly when it would be stable. And what would be the criterion for that? So I would like to have d over dx of f2 of x at x equal to a or x equal to b. I would like this to be less than 1 in magnitude. So it is easy to see that since this thing could also be written as df over dA, let us call it x1, sorry, dx1, sorry, so let us x2. So what I have here is a situation where f of x1 equal to x2 and f of x2 is equal to x1 back again. And if you have a situation like this, you could rewrite this in this fashion, and if the modulus is less than 1, the product is less than 1, then you have a stable fixed point, a stable period 2 cycle. Okay. A moment's thought will convince you that this is right. All I have done is to write this as f of x, and I have called f of x some other variable. So it is df1 fx1 over dx1, dx1 over dx2. So all I do is to differentiate a second time, and this is it. Similarly, you could have a period p cycle. So an orbit which goes from some value a1 to a2 to a3 to ap back to a1, and the set of p points a1 to ap forms a period p cycle, which is stable if the magnitude of the slope of the pth iterate of this function is less than 1 at any of these periodic points, or written in this fashion, if the product of the slopes at all the points on the orbit is less than 1 in magnitude, then you have a stable period p cycle, and if it is greater than 1 it is unstable. Once again you could have a marginal stability here. Now let us draw a picture and see when this happens and how it goes on. So we need to write down right away some kind of function which would do this, and here for example let us specialize to the unit interval in the x axis. So let me plot f of x here versus x here, and we focus on just the unit interval, and let f of x also take values in the unit interval, and then we ask what does this function look like, what are its fixed points, and so on. So let me take a very typical function which we are going to study in some detail. So here is the bisector, and suppose this function is like this, some function with the single hump on top. Here is the fixed point, and here too is a fixed point, and it is immediately clear from this picture that both these are greater than 1. If this is a symmetric parabola, for instance, this slope is greater than 1, this slope is greater than 1 in magnitude, and therefore these are unstable fixed points. On the other hand, if I iterate this function once, I go through the iteration once, what would the iterate look like? What would f2 of x look like? What would iterating this function lead to? Well, we can do this in detail, but perhaps it would do something like this fashion here. And there are now several fixed points, there is 1 here, 2 here, 3 here, and 4 here. What would these fixed points correspond to? This fixed point remains a fixed point here, so the fixed point of a map remains a fixed point of its iterates, that is quite clear, because if f of x star is equal to x star, then f any number of iterates fp of x star is again equal to x star. Under iteration this does not change at all, so the fixed point of a map is also a fixed point for all its iterates. The converse is not true in general, because if you look at this case, this is F2, it has 4 fixed points while F has just 2 fixed points here. Now it is quite evident from this picture that this was an original fixed point, it remains so. This point here is this, once again it remains so, but you have 2 new fixed points here. What would they correspond to as far as the original map is concerned? What would these 2 points correspond to? That would correspond to a period 2 cycle. The new fixed points would correspond to a period 2 cycle. So it would simply mean that if you took this value and found the map function, it would go to this value, and if you took this value and found the map function, it would come back to this value. So the fixed points, the new fixed points of the first iterate F2, they straddle the original fixed point of this map here, and it is evident from the picture in this case, at least pictorially it looks like all of them are unstable, but that does not have to be the case. It depends on the kind of function we are looking at. We are going to look at it in some detail, but I want you to appreciate the fact that period P cycles are fixed points of the pth iterate of the map, which are not fixed points of any of the earlier iterates. Just as this period 2 cycle is a fixed point of F2, which is not a fixed point of F itself. Okay. So now let us do some specific calculations to understand what this thing looks like. There are several standard maps. I should not use the word standard map because that is used in a specific context as well, but there are several so to speak typical prototypical maps which are studied in one dimensional dynamics, which are useful to know about because they illustrate many general properties, and let us start with a few of them and go on from there. The first of these is the so called Bernoulli shift, or the doubling map, or the binary shift, and it is as follows. So you start with a number x0 in the interval 0 to 1, the unit interval, and x1 is twice x0 modulo 1. In other words, double the number and subtract 1 if the number exceeds 1, and the general function, the map function, is xn is equal to twice xn plus 1 is twice xn modulo 1. Already this map has many interesting properties, and it is called the binary shift, or the one dimensional Baker transformation, or the Bernoulli shift, or the Bernoulli map, and so on. For ease of notation, for convenience, let me just call it the Bernoulli map. And it is given by xn plus 1 is 2xn modulo 1. Let us try to draw a picture of this map. So here is the unit interval 0 to 1, and here is x, and here is f of x, which is 2x modulo 1. And as always, I draw the bisector first, and then I start with this number. All I have to do is to double this thing, so it is a straight line with slope 2. So at the point half, the map function has already crossed 1, and then it would go on like this up to this point, up to 2, but then we are told you have to subtract 1 if the number exceeds 1, and that is equivalent to taking that piece, cutting it, and putting it back here. So I should draw it as a straight line so it does not look like it is a curved line. The slope is 2 everywhere. Is this a linear function? Would you call this a linear function? It is piecewise linear. It is not linear, it is piecewise linear. This piece is linear, this piece is linear. Is it continuous or discontinuous? It has a discontinuity at this point. Does it have fixed points? 0 and 1 are fixed points, that is very clear. Are they stable or unstable? They are both unstable because the slope is equal to 2 in magnitude at each point, and therefore these are both unstable fixed points. Okay. What happens, perhaps this has stable periodic points, we should check that out. So what does the double map look like? What is f2 of x? This is equal to 2 squared x modulo 1, because it is 2x modulo 1 and then another 2x modulo 1, double it once again, so it is 4x modulo 1. And what does this function look like? So here is a half, here is a quarter, here is 3/4, and this function looks like this, and this is the bisector. Where are the fixed points of this map? Well, 0 is a fixed point, so here we had fixed points 0 and 1, both unstable. The fixed points here, of course 0 and 1 are fixed points, but you also have 2 more. Where are these points? It is easy to guess here. All you have to do is to double this number and take modulo 1. So where is this point? What happens if you take 1/3? Where does 1/3 go when you double it? 2/3. And where does 2/3 go when you double it?
1/3.
Back to 1/3, because 4/3 you subtract 1, it is back to 1/3. So it is evident that 0, 1/3, 2/3 and 1 are fixed points of this iterated map, of which 0 and 1 are already fixed points of the original map, and 1/3 and 2/3 form a period 2 cycle. So this point jumps into that point jumps back into this, and it keeps going forever. Are these stable? Is this a stable period 2 cycle? It is definitely unstable because the slope is 4. The slope in fact is 4, definitely unstable. Are there any other period 2 cycles? Pardon me? Well, 0 and 1 are trivial period 2 cycles because they are actually period 1 cycles, they are already fixed points. So I said a period p cycle is a set of p points such that it is a fixed point of the pth iterate of the map, but not of any of the earlier iterates. Yes, so there are no other period 2 cycles here as far as we can tell. Okay. What about the next iterate? The slope would be 8 and you get a large number of fixed points, but you get a new period cycle as well, but the fact is that all of them are unstable. So it is immediately clear that all the points here, all fixed points of the map as well as all its iterates are unstable. Then the question arises, if a point does not belong to a periodic orbit, where does it go? On iteration, where does it end up? It turns out it wanders forever on the unit interval, never leaving the unit interval, but in a completely aperiodic and irregular fashion, in fact in a chaotic fashion. So this is our first example of what chaos is. We will define chaos much more precisely, but the fact is that you have an infinite number of points which sit on periodic cycles, all of which are unstable. So if you start with a point exactly at one of the points of the orbit of a periodic cycle, this point will move in this periodic orbit, but all other points, the iterates, will uniformly and densely fill up the entire unit interval given enough time. And this is an experiment you could do with pocket calculators. Start with a number, random number between 0 and 1 and iterate and keep doing this, and you will see that gradually its iterates fill up the entire interval. You could then ask, what are the points that actually fall on periodic orbits? we found that 1/3 and 2/3 falls on a periodic orbit. What about the point 1/5? Where does it go? Well, 1/5 would go to 2/5, which would go to 4/5, which would then go to 8/5, which is the same as 3/5, which would go to 6/5, which is the same as 1/5. So you end up with a period 4 cycle. The point 1/5 would go to a period 4 cycle, and so on. So let us generalize this. What is a sensible way of doing this? A convenient way of doing this is to write this x0 in binary decimal notation using the digits 0 and 1. So it is a number between 0 and 1, so let me write it as 0 point A0, A1, A2, A3 dot dot dot, where each AI equal to 0 or 1. If this is x0, what is x1? What is x1 equal to? I have to double this number, in other words multiplied by 2, and if it is greater than 1 I throw away the 1 part. If x0 is less than a half, then A0 is 0, because this is the coefficient of 1 over 2 to the power 1. If x0 is greater than a half but less than 1, then A0 is 1. At the next stage, when I multiply by 2, it is equivalent to taking this decimal point and shifting it there. That is all it does, because I have written it in binary. So it is immediately clear that x1 on doubling, so twice x0, is A0 point A1, A2, A3 dot dot dot, or therefore 2x0 mod 1, this is x1 equal to 0 point A1, A2, A3 dot. This is the reason for calling it the binary shift. All you have to do is to move this decimal point one place to the right and erase whatever is here. Is this map invertible? Is this map invertible? In other words, if I give you x1 as a function of x0, looks like this, or xn plus 1 as a function of xn looks like this, is this map invertible? If I give you an xn, you can find a unique x0, xn plus 1, but if I give you an xn plus 1, can you find a unique xn? No indeed, because if you give me a value here, I find the map function, or here I find this function, the next iterate. But if you give me the value of xn plus 1, there are two possible xn's from which it could have emerged. Regardless of what A0 is, you get the same x1. So the map is not invertible because it is not linear, non-invertible. Although it is piecewise linear. This non-invertibility is crucial, because it means if I give you xn and asked what x0 could it possibly have emerged from, there are 2 to the n possibilities, all of which would lead to the same xn. So you can see at each iteration I am losing a piece of information, I am losing one bit of information, because this gets erased. At the next stage A1 would get erased and you would have just 0 point A2, A3 and so on. So you have no way of going back and recovering what A1 was or what A0 was. So this plays the role of, this is responsible for many of the properties of this map, that it is not invertible, and moreover the number of pre-images of this map, the number of possible x0s which lead to a particular xn is actually increasing exponentially with n. It is 2 to the power n. Now let us see what are the points that lie on periodic orbits. Can we say that from here? What points would lie on periodic orbits? if it is part of a periodic orbit, it is clear after some time this pattern should repeat. What is the necessary and sufficient condition for that? Well, either this number terminates, either this expansion here in binary decimal form terminates at some point, after which you just get 0 0 0 everywhere, or it repeats. It is a periodic pattern by itself. What do you call those numbers? Rational numbers. All rational numbers between 0 and 1 would lie on periodic orbits, and all irrational numbers for which this never repeats itself would lie on the single chaotic attractor here. So that tells us at once that all irrational in this case it is the unit interval itself, the full unit interval is the chaotic attractor in a sense which will become precise in a moment. The rational numbers are dense on the unit interval, arbitrarily close to any point in the unit interval you can find rational numbers, so they are dense on the unit interval, but they form a set of measure 0. The total length of all the rational numbers is 0. You can count them off, they are denumerable, they are infinite but denumerable, you can count them off, you can put them into one-to-one correspondence with the integers.
So for
yeah.
terminating decimal,
Yeah.
The points only after some kth iteration lying on the periodic cycle.
So it is clear, that is a good point. He says that what if you have a system, what if you have a number where the first k digits are some specified digits and after that a pattern starts. What sort of object would that be? What sort of point would that be? It would be a point which after a certain number of iterations falls into a periodic orbit. So it is a pre-image of a periodic orbit. Would you call such an initial point rational or irrational? Rational, absolutely. Once again it is rational. It is just that it does not start off right away with a periodic pattern.
You say that it lies, all rational numbers lie on periodic cycles.
Yes.
It does not fully lie on a periodic cycle.
Why not? Why not? It is a rational number.
Yeah, the initial points are not a part of the periodic cycle.
Why do you say that? Why do you say it is not?
Only after you shift a certain number of decimals.
The pre-image, okay. We will come back to this question and answer. I want you to think about the answer to this question. What if I have k digits here which are completely arbitrary, and after that you have a 0 1 0 1 0 1 etc. After this many the next number is etc. This is certainly possible forever. What kind of number is this? And what kind of orbit does it belong to? So what would you say?
Again, pre-image of
Is this a rational number or not? It is a rational number. Therefore the correct statement is that all rational numbers either lie on periodic orbits or on pre-images of periodic orbits. A finite number of pre-images of periodic orbits. In other words, after a finite number of iterations all rational numbers would fall into periodic orbits. But the number of irrational numbers is infinitely larger than the number of rationals. It is uncountably infinite. You can't count, you can't enumerate all the irrational numbers between 0 and 1. Those numbers, the fate of those numbers is that they uniformly and densely fill up this unit interval, never hitting a rational point and never settling down to anything specific, any specific part of this unit interval, but always moving about, always wandering on the unit interval back and forth. So that is one aspect of this quote unquote chaotic behavior, which we still have to define precisely, which I will do in a very short while. The other aspect is that if you start with two numbers which are close to each other, then here is an instance where the error after n iterations becomes as large as the unit interval itself, and this is exactly what I said when I said we have exponential sensitivity to initial conditions. So it is very obvious that if you start with an x naught, so I start with an x naught and that leads after n iterations to xn equal to 2 to the power n x naught modulo 1, and I start with a y naught which is equal to x naught plus epsilon, and that goes to a yn which is equal to 2 to the n x naught plus epsilon modulo 1. So the separation between the two is 2 to the power n epsilon modulo 1, and if n becomes large, it is clear this number for arbitrarily small epsilon could become as large as the unit interval itself. So this was the statement I made, that there is exponential sensitivity to initial conditions, that the separation between neighboring points is in fact exponential in time. Remember that n is time, discrete time, and 2 to the power n is e to the n log 2. We would like to make that a little precise. We would also like to find out how are we sure that the iterates of these irrational points fill up this entire space, and finally we would like to ask what is meant by exponential sensitivity. So let us take that up next. So this is at the root of chaos. Now what I mean by exponential sensitivity to initial conditions, pictorially it means that if you start with an initial point here, and let me do this in continuous time dynamics just for pictorial for illustration's sake, and suppose this is the trajectory of this point, and I start with a neighboring point here, and let us suppose it is the trajectory here, then I would like to find out if points arbitrarily close to this point spread away from it exponentially fast or not as time goes on. So I would start with this initial distance here between them. After time t I would find this distance, and if this is exponentially a multiple e to the power some lambda t times this, then I would say there is exponential sensitivity, but I want to do this carefully. So how would I do this? And let us do this in terms of iterations, either discrete dynamics or continuous dynamics, it does not matter. How would I do this? How would I write this carefully? If this is epsilon and this is e to the lambda t epsilon, and I want to extract this lambda, clearly I take this distance, divide it by this distance, take the log, and then divide by 1 and divide by t in order to extract the lambda. So I define, yes.
What's the sanctity behind that a power x? Even some n factorial goes there.
What is the sanctity behind to what? To the exponential sensitivity? Okay. If the separation is a power law separation in time, like square root of time or time t itself or t squared or t to the power 20 whatever, then you can actually compute the difference, you can calculate the way the error amplifies in polynomial time. It is completely computable, but not possible if it is exponentially fast. In other words, no matter how small your initial error was, eventually things would blow up exponentially. And we saw in our study of dynamical systems, continuous time dynamics, that except at points where the vector field vanished, everywhere else the flow was actually exponential. The solutions locally were always of the form exponentials of time multiplied by some eigenvalues of some linearized matrix. So that is generic always, right. Besides, that is precisely the sort of separation which leads to amplification of uncontrolled amplification of errors, of initial uncertainties or imprecisions.
So does it mean that all linearizable system are fundamental?
If they, yes, it means that there is exponential instability. However, for chaos you need something more than that. You need to have that in whole regions of phase space, not at individual points. So certainly we can control what happens in most cases in regular behavior, but here it becomes uncontrolled. The error will actually grow till it fills up the system size itself. That does not happen in normal systems usually, okay.
So actually linearizability is actually a approximation of a nonlinear system.
The linearization is an approximation of a nonlinear system, yes.
Indeed naturally linear, it's chaotic.
The reason it became exponential there was because we had first order dynamics.
Yeah, so
We had first order exponential, we had first order dynamics, but the point is the system exponentially unstable in whole regions of phase space or only at isolated points? Just the fact that you have an e to the lt times x0 locally when you rectify a vector field does not imply chaos at all. You need many other conditions, which is.
So my question is, if the system had been inherently linear,
Yes.
that is, it's not an approximation.
Yes.
Then in whole regions of space it's exponential.
The solution is exponential, but the errors do not multiply exponentially in a linear system. They do not multiply exponentially in a linear system at all, right. You need nonlinearity for this sensitivity to happen. It is not enough to have nonlinearity, but a plain linear system, it does not do this at all, okay, because we are going to put down conditions for chaos. You have in mind a system of the following kind: x dot equal to x on the real line. The solution here is x of t is e to the t x of 0. Therefore, if I start with an x0 here, x naught here, then suppose here is x at time t, and I start with an x naught plus epsilon here, that of course will go to x naught plus epsilon e to the t, whereas this is xt is x naught e to the t, and this separation is an e to the t times this original separation. This is not chaos. This just says that the solution is an exponential. This is not chaos because the phase space is unbounded. Here. For chaos, we are going to define it for systems for which the phase space is actually bounded, and yet you have amplification of errors such that it mixes up in the space so badly that the error finally amplifies to the system size itself, the size of the phase space itself. That is not happening here. This is integrable, completely integrable.
So there is no concept of chaos in unbounded systems.
There is a concept of chaos, but it is not very interesting. If the exponential instability is because of an unboundedness in some phase space, in some axis, that is not very interesting because the system itself is integrable. So you will see what else is needed in order to produce chaos.
But there can always be systems which are not integrable but unbounded. Right?
Yes, though they would be chaotic.
It is going to be as difficult to.
As difficult, yes, I agree entirely, but they are not very interesting because there we know the system is unbounded, and that is the reason why things are becoming exponentially large. This is not very interesting. Yeah, we are looking at systems which are not integrable, that is very clear. Chaotic systems are not integrable in general, okay. Again I need to qualify that, we will come back to this in the case of discrete maps. So I want to define here this multiplier lambda in a careful way. I want it such that it is a property of this trajectory. I want to see how things are thrown away from it as you go along. So if you have a neighboring point here, that is thrown away. If you have a neighboring point here, that is thrown away. Another one here is thrown away, and so on. and I want to probe the rate at which it is being thrown away. So let me define it in the following way. I start by saying I have an initial point x naught and an initial point x naught plus epsilon here, say, that is my initial distance, and if after time t this point x naught finds itself at xt and the point y naught finds itself as at yt, then I compute modulus of yt minus xt divide by y naught minus x naught in this case, and in doing so I have got this e to the power whatever it is, I have got this. I take the log of this that brings down this exponent and I divide by a 1 over t, and that is supposed to give me this lambda, but I need to make sure that I am on this trajectory back here. So I go to the limit in which epsilon goes to 0, recall that this is equal to epsilon, and I need to do this, and this is supposed to be the asymptotic behavior, so I take the limit as t tends to infinity of this quantity, and that is my lambda. This is the definition of the Lyapunov exponent. Okay. I want you to pay particular attention to the order in which these limits are to be taken. If I do not do that, then it is clear that if the phase space is bounded, this number here is always finite, and then I have a whole lot of points, it does not diverge or anything like that, and then I take its log, divide by a t, and as long as this is finite the whole thing goes to 0. On the other hand, if epsilon goes to 0 first, you may have a very non-trivial lambda, this limit may exist and give you a non-trivial number, and that is the one we want to calculate. But for maps we could write a similar thing, this was for flows. For maps what would you write? Again I would write lambda is equal to limit n tending to infinity limit epsilon tending to 0 1 over n the log of the nth iterate divided by that would be my definition of the Lyapunov exponent if it exists. Now our map function says xn plus 1 is f of xn. So what does this become? This becomes equal to limit n tends to infinity limit epsilon goes to 0 1 over n the log of f nth iterate of x naught plus epsilon, because that is the nth iterate of y naught, minus f nth iterate of x naught divided by epsilon. But what is this equal to? We could simplify this. It is very clear that if this map is assumed to be differentiable, then what happens? So coming over from there, therefore lambda is equal to limit n tends to infinity 1 over n, and then what do we write here? Yeah, it is just the derivative at the point x naught. So it is equal to log of the derivative over dx at x equal to x naught. That if it exists is the Lyapunov exponent, and it is a function of the starting point. So it is in fact definitely a function of the trajectory on which, or the orbit on which x naught finds itself. Could change from one orbit to another, most certainly. But what do we have here? Remember that x1 equal to f of x naught, x2 is f of x1, and so on, xn is f of xn minus 1, and so on. So could we not write this in a simpler form? We would write this as limit n tends to infinity 1 over n, the log of, so let me write this dfn x, what is fn of x? It is just x sub n, right. So this is equal to df of xn minus 1 over dxn minus 1 times dxn minus 1, which is df of xn minus 2 over dxn minus 2, and I keep going down all the way, df of x naught over dx naught evaluated at x equal to x naught. Agree? But that can be simplified a little more, and you can write this as equal to limit n tends to infinity 1 over n, a summation from j equal to 0 to n minus 1 f prime of xj log Agreed? So it is just the time average, this is an average over time, it is the long time average of the log of mod f prime of x at all those points on which the initial point x naught falls as you iterate in time over a very long period of time. What is this for the Bernoulli shift that we just looked at? What would this be? What would this be for the Bernoulli shift? It could become an integral, yes, we are not sure yet, but we have, yes, we should be able to convert this to an integral, but then you have to say over what and so on. But this can be computed very easily for the map we just looked at, the doubling map, the Bernoulli shift. Well, the map was just 2x mod 1, and what is the slope? It is 2 everywhere, the slope is 2 at all points on this map, and therefore you get 0 to n minus 1 log 2, and you got to divide by this, so what is this equal to? It is log 2, and this system is exponentially sensitive to initial conditions. Could turn out that lambda is 0 in some cases, could certainly turn out that lambda is 0. Incidentally, if you had a power law separation between two trajectories, what would you get here? What would you get? Suppose you had an error which increased like a power law. Remember in our map here, xn was 2 to the n x naught mod 1, and yn was equal to 2 to the n x naught plus epsilon mod 1, and what we found was this amplification of this error 2 to the n epsilon, and we got this, we essentially found this, we wrote it as e to the n, this quantity is e to the n log 2, and we detected this log 2 there. If instead of 2 to the n x naught plus epsilon, suppose this went like n squared, what would happen if you went through this process? We have a power law separation now, and instead of errors amplifying n fold, suppose the initial precision imprecision epsilon goes to epsilon times n to the power k. Yes, when I take this and divide by epsilon, this goes away. When I take the log, I get k log n, and then I have log n over n, and the limit is 0. So this method, this definition of the Lyapunov exponent, is geared to find exponential instabilities. It does not mean that trajectories have to stay close to each other, they could separate sub exponentially, and if they did that, you detect 0 Lyapunov exponent. Lyapunov exponent would just turn out to be 0 in those cases, could even turn out to be negative. We are going to see instances of that, we will see the physical interpretation of what happens if things become negative, but you can actually guess. Suppose I find a lambda to be negative, what would you conclude? Yes, absolutely right. I would conclude that things are converging exponentially rapidly, either falling into some periodic orbit or into some fixed point which is stable, exactly. So I would immediately detect stability if I had negative Lyapunov exponents, but if I have a positive Lyapunov exponent, it certainly implies chaotic behavior. We will define chaos carefully, but now the time has come for me to say what the definition is. I will repeat this again. We want a finite phase space, we want exponential sensitivity to initial conditions in the sense of one or more non-zero Lyapunov exponents, and finally you want a dense set of unstable periodic orbits buried in this phase space, and that is what throws things aside on both sides, exactly like a separatrix does. The statement was, and I will repeat this again because we are over today.